So we're going to go a bit further, further down, close to the ground, and going back down to Earth and burst Rico's bubble. So what I want to present is we actually been approached by an International Geological Survey Organization to develop a new open source piece of code, so software, to better build 3D models of geology. So the static models, the geometrical models, and they're based on field observations that geologists do. This is my bread and butter. This is a very long list of people. There should be some people from the Mathematical School of Science as well associated with that, so put your name down here, please. And I'm not going to go through the list, but most of these people here are geologists, so we like to go in the field, measure stuff, look at the rocks, have an idea of what the 3D geometry of the rocks do under the ground, and then we put that in a computer. In the past, we used to do it by basically meshing cross-section together. So we do an interpretation. It's very highly interpretative, very uncertain. And we used to put triangles in between cross-sections to represent surfaces. Those surfaces are the boundaries between different rock packages. So that's what we want to represent. Some of these people are mathematicians. How do I... yeah. That's the only way? Yeah. In recent years, so basically 10 years ago, there was methods that are called implicit 3D geological models or modeling methods that were invented. Basically, it's a mathematical representation of the geology of those interfaces using scalar fields. So it's a mathematical formulation of the models, then you have to render it to look at it. But those techniques have been only applied to basins, so very simple geometries, layer cakes. I know you're not geologists, but they're very simple geometries, and they're not applicable to what we want to do, which is looking at polydeform areas like the Alps, the Himalayas, or very deformed areas where we happen to also find the mineral resources that we live on. So the project has got 5 modules. The first one is sort of irrelevant to us. It's going to be dealt with by the geological survey organizations. We have a phase of data processing, or an upstream phase where we're going to have to capture the time and the topological relationship between geological objects. And I'm going to hopefully explain that a bit more in the next few slides. We're also going to look at how we can upscale our data, because very often we go in the field, we map a very small area, we have lots of data here, but it's not all of that data is relevant or needs to be upscaled to the scale of the model we want to build. The module 3 is about basically building the core algorithm to integrate all of that data into a geometrical description of the Earth. We've done a bit of work already on that, and I'm going to show you examples. And it's cool. Module number 4 is about uncertainty. So as I said, even the observations in the field are highly uncertain, they're highly interpretative. And we need to be able to simulate, so to propagate the uncertainty from the data and basically do geological simulations. By doing so, we're going to build millions of models. We should be able to classify them using machine learning, self-organizing maps, things like this. So basically using geodiversity metrics. So we're using geodiversity the same way the biologists use biodiversity. So we measure geometrical characteristic of the, or topological characteristic of the models. And we then classify the hundreds of models or millions of models into categories, into classes. And I think this is more for the future, but if you're interested, please, you're welcome. We also need to be thinking about the application of the model. So it's not, we just don't want to build 3D models to look at them and spin them in the computer. We actually want them to be useful for further modeling. So for example, fluid flow, hydrogeology, so looking at the water resources, which is going to be very important in the future. And basically it's looking at clever meshing algorithm and then solving equations within those unstructured meshes, for example. So, what have we done so far? So this is the principle of geological implicit modeling. This is one of the software available that works fantastically for basins. You're looking for interfaces between different rock packages. So the dots here are observations of one of these interfaces. So we have 2 interfaces between basically 3 formations. Yeah, you can imagine the interface is going somewhere through here. So that would be formation A, formation B, and then another interface through here, that would be formation C. We're interested in defining those formations, those boundaries in 3D. What we have as well is we have the gradient of the position of those observations. So it's basically what we measure in the field. We call it the strike and dip. It's basically the orientation of that plane as we can see it at the surface. The data can also be derived from seismic interpretations, from potential field interpretations, so magnetics and gravity. So we have multiple ways of deriving that information. But basically, we end up with a system where we have the value and the gradient of the value of a scalar field that we then use co-Kriging to calculate in 3D. And your isosurfaces or your iso value of the scalar field becomes your interface in 3D. For geological problems, we actually also have faults, and so faults are discontinuities in the rock packages. So we need to take them into account. Obviously, when you interpolate, then those discontinuities become a bit of a problem. But you have to define the topological relationship between the faults, so which faults terminates on which fault intersect which other fault, and also define the relationship between the faults and the different packages of rocks you may have in your model. The other thing we need to define, and it's all to do with topology, is the relationship between different series of formations, if you want, and each of the series is going to be modeled with a different scalar field. So you need to combine different scalar fields to end up with a model. Yeah, so for example, here you have an intrusion or a granite, if you want, and this granite has been eroding everything else when it was in place, so removing everything else. So the relationship is basically an intersection relationship. Yep. Ta-da. So this kind of information can be derived semi-automatically by looking at geological maps. So this is here a very simple example of a map in the Pilbara. And what you can see here, you got basically a topological relationship between different units. And what Ogarko 2016 has done is basically created what we call a stratigraphic pile, which is the relationship between different formations, so rock packages of different age deposited at different times, and it also represented the type of relationship of those different packages. So, for example, in blue, these are conformable relationships. So a package was deposited on top of the other package, and in red, it's a relationship where the two formations are found across a fault. So discontinuity in the geology. The width, well, it doesn't really matter, but the width is basically representative of the length area on the map of the contact, of the different type of contacts between the different formations. Yep. I'll go back to that because this is actually important. When we think about uncertainty, in geoscience, we have three main types of uncertainties. Basically, the first uncertainty is about the inherent uncertainty of the measurement of the data. So the location, the representativity of the observation with respect to characterizing the geometry of a given unit. And yeah, so this uncertainty is inherent in the data, and we need to be able to simulate it and create multiple models from that. The other type of uncertainty is an algorithmic uncertainty. So we use co-Kriging, or we use radial basis functions algorithms. They all have different parameters that you can play with, and you can actually change the way the interpolation of a given surface is going to be done depending on the algorithm. And this actually is not geological, so we want to try to avoid or to understand what the algorithms do to the models. And the third type of uncertainty is the unknown. So what if you have a fault that is not outcropping? So what do you have something that you actually don't know anything about? You don't even know if it can exist. And this is where we need to be also able to run simulations. In fact, we need to run simulations for all of these things. So when I was talking about the topology, it was a very simple system where it was back to a basin system. It became even more complicated with deformations. So when you take a piece of rock and you shorten it in that direction, you're actually going to deform it. So for example, you can make a fold. Yeah? The fold is characterized by the foliation that's folded. Here it's the layering, the bedding. It's also characterized by geometric elements that we measure in the field. And these are not taken into account in software yet. So this is what I call the actual surface. So it's in the axis, or it's a bisecting, the bisecting plane in between the two limbs. And you also got a fold axis, so it's a line that basically follows the maximum curvature of the fold. That line can go like this as well. These structures can be refolded. Yeah? And so we need to capture that information. So the first phase of the project is going to develop what we call a geological event manager, where we're going to have to capture the stratigraphy and capture the structural evolution of the terrain. Ta-da! Yeah. So I'm going to show you examples how we deal with polydeformation. And by polydeformation, I'm talking about polyfolding, so multiple event of folding. We actually cannot take care of or take into account faulting yet. But basically what we do is we have this actual surface. So this is my plane of symmetry of the fold. And this is derived from data. So you can interpolate this. If this is the latest deformation event, it should be straightish. Then you look at the foliation. So if you have a two folding events, sorry, I should go back to the beginning. If you have two folding events, you're looking at the F2 is your fold of generation 2. It's associated with a foliation or an actual surface, which is that straight field through here. Then you look at your data for the measurement of your S1, which is another foliation, which is just holder, and that's refolded by those folds. You can combine the field of S2 with the measurement of S1 to extract the fold profile, sorry. And once you know that, you can then calculate the field of that S1 foliation. If the S1 foliation was also associated with another folding event, then you can calculate the field. So for example, if you combine that field of S1 with the layering measurements, you can extract the fold profile of that layering the fold profile of the first deformation event, and then calculate the field of the layering. So calculate basically the geometry you're interested in. Yeah. This is something we can do at the moment, but we can't deal with discontinuities. We think we have an idea, but I would love to hear your ideas. So I'm going to actually pass how we do it, but basically, yeah, I'm going to go fast through that. But we're using geostatistics, and we're using fitting of curves. I'm going to pass this because that actually doesn't really matter. Maybe it does, but we can go back to it if you have questions. But it does work. The advantage of this is we can also run simulations straight away on the fitting of the profile. So for the folding and the polydeformation, without discontinuities, we know what we're doing, I think. Come on. All right. What's also of interest, so if we can generate multiple models, we are interested in looking at the uncertainty of the models created. At the moment, we use a stratigraphic variability, which is a very simplistic and maybe too simplistic way of capturing the variability between different models. So if you imagine we have a model, it's made of voxels, and we've extracted out of 8 models, we've extracted the same layer, so a slice through the model, and extracted the different lithologies in that same layer. Then we just count how many occurrences there are of the same lithology. And so for example, here we have 2 gray ones, 2 darker gray, and 2 black, and 4 black occurrences. That give us a stratigraphic variability of 0.5. Yeah? We can also use information entropy, which I think is a bit more powerful, as information entropy captures the variability of the many different occurrences you can have within the same model at the same location, within the series of models at the same location. This is somewhere where this is a field where I think we need to do a lot of improvement, because we've been doing this in as it came. Basically, we're not mathematicians. We just thought about, oh, let's do this or let's do that. And I think there are better ways to characterize uncertainty in models or variability in grids, basically. Another way, so to classify the models, we use what we call geodiversity. And geodiversity is basically looking at the models and trying to quantify one aspect of the model, so give each model a number for a given variable. So for example, you can do a short distance neighborhood relationships, and you sum them up, or you do some, are we already done? Woohoo! So it doesn't matter. The important thing is, so we can use all these things, we can do simulations. I'm sure you guys know what I'm talking about. We get a meshing. More importantly, this is where we need the mathematicians. So we need you guys. So we need you guys for a topology and basically a time-aware topology. And we need to be able to capture that. This is, I think this is the core of the software, is going to be able to capture a system, or to have a system that captures the topological relationship between different objects and the time evolutions of those relationships. Once we can do that, then we'll have an issue with data fitting with discontinuities. How do we deal with faults? How do we deal with discontinuities that may end up being bent or folded during later deformations? And that's really what we need at Monash. I think this is what's going to be developed at Monash. But we are also very, very interested in optimization of the geodiversity matrix. We actually don't know which metric should be used in what type of models. Are there different type of metrics to be used in different type of models? And how do you classify the different types of models? So there is a lot of unknown in what we're doing. And another thing is about the interpolations. So at the moment we use radial basis functions, we use kriging and co-kriging, but somehow we think that those foliations we're trying, or those surfaces, those boundaries we're trying to model are made through a physical process, that we think there should be a link between the physical process that makes the foliations and some mathematical function to interpolate those boundaries. So this is where we actually have no idea. We think there is something in there, but we have no idea how to do it. So thank you very much.
Thank you.
What's your name?